So we want to pick up talking about the hydrogen atom in the Bohr model. So the Bohr model is you have a nucleus down here and then you have shells where the electrons orbit around the nucleus as if they're planets. And his model explains something that we were seeing in the hydrogen atom that no one had really figured out at the time. And that was that when you excited this atom by like shooting electricity through it or getting it really, really hot or lots of other things, what would happen is there'd be emission of certain wavelengths of light. So what he found out, or what he said, is that, for example, if an electron fell from shell 3, so let me label the shells for us really quick. This is shell n equals 1. That's our nucleus way down there. N equals 2 is shell 2. N equals 3 is shell 3. N equals 4 is shell 4. He found that when an electron falls in energy level, that a specific wavelength of light is emitted. And if it fell a different energy level, then a specific wavelength of light that's different and higher energy here, because it's a higher drop, would be emitted from that fall, etc. And he said you can calculate that wavelength that's emitted by this equation. 1 over lambda, 1 over the wavelength of the emitted light from the hydrogen atom equals the Rydberg constant times 1 over Ni squared minus 1 over Ns squared. Ni is just the initial shell that it fell from, so this would be, in this equation here, would be, or for this drop here, would be the third shell to the second shell. So you just plug in the third shell here and the second shell there. So what was so great about that? Really, well, what's great for us about it, really, is that this is our first look at what a quantum number is. So the shell is a quantum number, meaning the electron can be in shell 3 or it can be in shell 2, but you can't like fall to shell 2.5 or shell 1.5. Those transitions don't exist. We never see light emitted from anything in between. It's only either shell 2 or shell 1, or shell 3 or shell 1, that kind of thing. And we can observe all of those emissions of light as long as it's a whole number that you're plugging into this equation. But we don't observe any emission in between from a hydrogen. So that's what's really cool. This idea that an electron has specific levels within a hydrogen atom it can be at. That's the idea of quantum numbers. There's this quantity, and this quantity, and this quantity, and this quantity, and you can't be somewhere in between. So, I mean, on its surface, that's all this equation is good for. It's just good for determining emissions from different energy transitions in the hydrogen atom. And it's great, it's really easy to use because it works out the same way every time. The algebra is a little tough the first time, but it works out exactly the same every time after that. So you just plug in the Rydberg constant, which is 1.097 times 10 to the 7 inverse meters. Then the shell that you want to transition from and the shell that you want to transition to. So if we were to calculate that first one, and you would plug in 3 there. So for the 3 to 2 transition, you would get, you can plug into your calculators and check me, but you're going to get 656 nanometers. Or actually, it's going to come out in just meters. So what you're going to get is 6.56 times 10 to the negative 7 meters, which is 656 nanometers. If you did it for the second one we did there, from the fourth shell to the second shell, you would get 486, etc. That just tells you what wavelengths of light are emitted from the hydrogen atom. So there's a cool modification of this equation that sort of gets us to what you were seeing in Mr. Velo's video. So it turns out that when you see the equation in this form, 1 over lambda, that might jog your memory It probably doesn't, but another equation we've been using, it did people who were doing this kind of work, because they were using these light equations all the time, and they saw this light equation that looked like this. You can calculate the energy of a photon of light. So this is the wavelength of a light, right? But you can calculate the energy of that photon as just hc over lambda. So that's already dividing by lambda. So if you try to merge these two equations, then you can calculate the energy of the photon emitted as just, we know a photon is hc over lambda, so that's h times c times Rydberg's constant. So you just add two more constants to the equation, and instead of calculating the wavelength, you're calculating the energy of the photon emitted. And there's one more thing we want to do with this, but let me just pause here. So it's the same equation, we just added two constants in and turned an inverse wavelength into an energy of light. So using this equation, we could just directly calculate the wavelength. Using this equation, we could directly calculate the energy of that light. Make sense? Sort of? Well, here's the neat little connection now, and you'll see it connecting back to Mr. Bale's video, is that the energy of the emitted photon has to be the energy of this photon. Photon is just one individual piece of light that's shot out. The energy of that light has to be equal to the change in energy level of the electron. So the amount of energy that this fell down, that's the energy of the emitted photon. I always tell people to think of it like this. I'm going to drop my pen, and what it's going to emit when it hits the ground is a sound wave that's going to travel to your ear. It's going to bounce some atoms and molecules into each other. It'll vibrate through the air and hit your ear. You heard that? Okay, so that's for the energy transition from here to there. What about if it was from the energy transition from here to there? Louder, right? More energy transmitted. So here to here is that much. Here to here is that much. Here is that much. So you're getting more energy out depending on the energy level transition. Same kind of thing here. This size of energy directly relates to the energy of the photon. It's the same as the energy of the photon emitted. This amount of energy difference, if it falls this far, that amount of energy difference is directly put into the photon, which is emitted. So we could just add one little term to this equation and say that is equal to the change in the energy level of the electron. And this would be a potential energy, right? Because the pen had potential to turn into kinetic energy as it fell. So the difference from here to here is a potential energy difference. When it falls, it turns into the kinetic energy of the light. So ultimately what you can do is you can actually separate this out. If you propagate this term through, so let me move just down here a little lower. I don't want to keep in the same chain. We're talking about the change in energy of an electron. So that's like the energy final for the electron minus the energy initial for the electron. That's a change in energy, right? A change in something is always a final state minus an initial state. So if we multiply hc over rh times that, h times c times the Rydberg constant over ni squared minus h times c times the Rydberg constant over nf squared, you can see how the terms line up. And it's pretty neat. That the final energy is actually this term here, just like the final shell. And the initial energy is this term here, like that shell there. So that is how Mr. Balo is calculating those energy numbers that he said This shell is this energy. This shell is this energy. This shell is this energy. That shell has this energy level. That shell has this energy level. And so the difference between those energy levels is the amount of energy that must be put into that photon that's emitted. And you can use any one of those forms of that equation, but that's all the sort of discussion that they were having, trying to understand how light was emitted from atoms and how the energy levels of an atom correlated, and why these specific constants of 1 and 2 and 3 were going into the equation, but not 2.5, not 2.2. Only the integer values go into the equation, and it all sort of led to this kind of reasoning overall. And we can calculate whichever one of those things we're interested in knowing. Any questions?
All those are only for the Bohr model?
Those are only, that's the terrible thing. Those are only for the hydrogen atom, specifically.
This whole thing?
Yeah. So it can be expanded to anything with just one electron. Because as soon as you have more than one electron, that's when you have to take into account the other quantum numbers, so the equation gets more complicated. So notice there's this little h next to the Rydberg constant. That's the Rydberg constant for the hydrogen atom. If you had anything else, like a helium 1+ ion that had just one electron, you could just change this to the Rydberg constant for the helium atom, or the Rydberg constant for the lithium 2+ ion, or something like that, that has just one electron, and use the same equation. But as soon as you get two equations, that's when you have to start taking into account those other quantum numbers, the L value of the electron, the M sub L value of the electron. And that adds terms to this equation, and the math gets so messy that you don't ever want to do it. So that's why we start showing you those pictures of what the orbitals look like, and you don't have to calculate this. But this is it's really good to work through this idea, because it helps us understand how electron transition turned into energies of light, and what the idea of a quantum number is. It's a simple equation, relatively simple equation, but you can see what the idea of a quantum number is without having to go to the equations that take complicated calculus to understand. Questions? Other questions? Okay. Thanks. I'm going to stop the video and then